Hello everyone. This will be a live speed demo of our Libstorage stack for Docker Engine. Libstorage to Docker Engine defines volume lifecycle management. It has been integrated with Docker Swarm as well, and Libstorage is distributed by itself, considered similar to libnetwork. To prove my point, I shall work with either of local Docker Engine or with the Swarm engine. So we have in this test scenario a 8 node Swarm cluster. Let's get on with the extension that we have done for Docker through our Libstorage. We have included a ds volume subcommand under Docker, which includes all the extensions that we have done for volume extension. There is a top level create, remove, list and information on volumes. Apart from that, the core functionalities of snapshots, rollbacks and QoS for volumes are also available. So let us go ahead and create the 4 volumes on cluster with different policies. We have policies defined on the volumes. Every volume can be either distributed or local or a RAM or a secure volume. Each of these policies define how the volume content should be available across nodes in the cluster. The first case, we created a distributed volume whose size is 100 megabytes and the name of the volume is my distributed. Note that this has been given to Swarm engine to create. Then the next policy was a local, and my local volume was created over it, and the sharing flag on that particular volume has been disabled, which means if there are multiple containers wanting to use that volume concurrently, then they will be disabled. They will fail to access the volume and the container spawning will get failed. Now there is a RAM volume where the volume is backed up by RAM. So as long as there is a reference to a container acting on the volume, the contents will be available. When there is no containers using the volume, then the RAM volume will get destroyed. Similarly, there is a secure volume where the policy of sharing is implicitly disabled, which means my secure volume is backed up by a ROM volume and cannot be shared by any other containers on the same node. Now let's go ahead and run docker ds volume list. This lists all the containers available on this particular node, on the cluster rather. So you can see that this command has been given through the Swarm engine and it listed all the 4 volumes that you have created so far. But there is a created node and that is different for most of the volumes. We see that the my distributed volume got created from node dolphin host 5. This is because the Swarm engine can pick any of the nodes in the cluster. Since Libstorage is distributed, it doesn't matter which node it picks to actually perform that operation. To drive home this point, let me open up a shell on a different machine. So now that we have actually logged into a Dolphin host 8, which is part of the cluster. Now I run the volume management command ds volume list. This is a direct command to the local Docker engine. And you see that all the volumes are available here as well. This proves the distributed nature of Libstorage. Now let's go back to continue with the demo. We will now mount all the 4 volumes that you have created using a Swarm engine. Now that we see that all the 4 volumes are mounted inside the container. Let's look and grep for the volume properties alone. Here. So we have all the 4 volumes that have been used to create mounted within this container, and the properties are available from the mount system call. So we see that OPT distributed is a distributed volume and it is mounted from the device dev RBD0, and secure and RAM or tempfs, which are RAM volumes, and local is nothing but it's a local directory or file system on the host machine. One aspect that we would like to show here is if the backing volume is a block device, then that block device is also directly accessible from within the container. In this case, we see that there is a block device called my distributed, which is the backing block device for my distributed volume OPT distributed, my distributed, right? So currently none of the Docker engines has support to direct block level access to volumes. So we can create volumes to actually provision and as containers to use them directly as raw block devices. Now the other aspect that I would like to see is how does the volume properties change for all of these as containers use. Let's open up a new terminal and then I'm going to show the properties that we would like to see on a volume, especially given that now all of these containers are currently being used. So we see that the container is being used in host 2 and the container ID is this. Now let's go back. So what that MySecure does is, if I were to go to Dolphin host 2 and then try to mount this particular volume within a container, let's say I would call it a spoof volume, and run a bare minimum Ubuntu, it should fail because sharing is not configured for this volume. For secure volumes, there is no way the sharing attribute can be disabled. And additionally, we would like to see some of the properties here. The volume also keeps track of which all nodes in the cluster is using this volume and which all containers are using this volume. We will look at when these additional properties are getting updated soon. So now let's go back to continue with our demo. So now that we are inside a container with 4 volumes mounted. Now let's go to our distributed volume and then try to dirty the contents. So let me pull in some files here. So let's keep this as a first update and copy some files from the host machine into this, rather from within the image. So now that we see that this particular volume has contents that mentions at least this is a first update. Now let's go back to continue to create a snapshot on this volume. So creating a snapshot can also be done from any node in the cluster. So let's go back to listing all the volumes that is available there. To create a snapshot, let's run my script. The script is nothing but a CLI extension running docker ds volume snapshot create -p volume distributed and the snapshot name. The creation of volume passed with no issues. Now let us list all the snapshots that's available. We see that my distributed volume has got a snapshot mysnap1 and it is created from Dolphin host 6 this node. So let's go back now that we have done with the snapshot creation of our volume. So remember, the contents of the volume should have first update. That was what the contents we used. Now let us go back and create a new container on this volume and then modify the contents to move further away from the snapshot. So let's go to distributed. We expect the contents to be first update. This, as expected, the contents are available. Now remember, I'm invoking this through a swarm engine. Now I'm removing all the contents. Now I'm modifying the contents to have a second update. And for my second update, let me copy some log file into it. So this is the second update of my volume. So this particular volume, my distributed, had a snapshot taken after the first update, and now the container has actually diverged the volume contents to a second update. Now with this volume, we will go back to see how a rollback works. So now let's do a rollback on the same volume, my distributed, to earlier snapshot taken on that particular value, my snap1. So after the end of this operation, we expect the contents of that my distributed volume to be similar to the first update. Now let us mount this volume inside a container and then look at OPT distributed. We are since this is a rollback operation that we had performed on this volume, we expect the contents to be a first update instead of the second update. There, we have a rollback on the volume successfully done. Now let's back and try to do a clone on the snapshot. So we can do a clone operation on a particular snapshot too. So docker ds volume snapshot clone. This is the volume name and the snapshot name and new volume property. So the name of the new volume is first clone. So we could see that this is the information on first clone. So we see that these properties got updated specifically. Is it a clone? Yes. And the parent snapshot for this volume is my distributed at snap1. Now let's actually see the contents of this particular clone. Since this got cloned from the first snapshot, the contents of the OPT my volume should match my first update. There it is. The cloned snapshot volume is similar to what the earlier snapshot was taken. Now let's go and look at how QoS is applied on volumes. Now always there is a default QoS available, and then there is a demo QoS that has already been created here. Now we can go ahead and edit the QoS as well. So in this case, after modification, you can see that the default QoS has properties changed. Now we can also go ahead and create a new QoS policy. In this case, the demo QoS, since it's already available, there is an error that's seen. Now let's take this demo QoS policy and then apply it on volumes. As a first step, since we are going to do a demo on volume performance, I would want a raw access to volumes. So to prove that, how the bytes per second bandwidth property is actually applied. So I go ahead and first create a raw volume. This is also currently not supported, as mentioned earlier, with any of the Docker engines, with the standard Docker engine. We can create a file system as raw, which means this volume can only be directly accessed as a direct block device, and the size of the volume is 50 megabytes. Let's go ahead and do this volume creation. The volume creation was successful with no error. Now let's go and apply the QoS policy demo QoS on this volume demo raw. So you see that docker ds volume QoS apply this policy demo QoS on the volume. You could have more than one volume getting applied with the same policy. Now let's look at the properties of this particular volume. We created this demo raw volume, which is a raw volume in the sense that there is no file system on top of it. It's a direct block level access. And we also see that the QoS state and QoS profiles are applied successfully. Now let's go ahead and use this volume inside a container. Now we have mounted a demo raw volume into a container. Now let's run some profiling of performance. Remember that demo QoS can only do up to 22k bytes per second. So if I were to actually read from dev demo raw output file is, I'm going to throw away all the output. I'm more concerned about how fast the operation or how long it takes for this operation to complete, and I'm going to read 640 kilobytes of data, and this operation should ideally take around 30 seconds with the QoS that is applied. So this is how the QoS gets applied on containers. Rather, okay, it's not 4, it is 40 seconds, right? So this command tells you that I will write 640 kilobytes of data. The earlier operation was a 64 kilobytes of data. So for this operation, we should ideally be taking around 30 seconds. So let's go back. Just as a rough estimation, we know that our read operation was 2222 bytes per second, and we are going to do it for around 30 seconds. This is the total number of bytes I can read, and divided by 1024, so many kilobytes, which equals to 640k. There you go, around 39 seconds of, it took around 39 seconds to complete that read operation. So now if you were to contrast with how the QoS is really working, let us disable the QoS on this volume and then perform the same operation on a container that mounts this volume. Now we see that the QoS state is actually disabled. Now I'm going to mount this volume inside a container. Now run the same command dd for 640K. Remember earlier it took around 39 seconds based on our back of the hand QoS calculation. Now this is the raw host performance, which is not even around 16 milliseconds. So that is how containers, we can apply QoS on containers. So this is how we have actually performed QoS for containers, that is accessing volumes on a shared system. So I hope you liked the demo.